again to this presentation. Now we are going to start on question number 11. Last time we ended on question number 10. Question number 11 is saying, explain why a buffer can be prepared from a mixture of ammonium chloride and sodium hydroxide, but not from ammonia and sodium hydroxide. So to solve this question, we need to know what is a buffer and what is the composition of the buffer. Now, what is the buffer? To get the buffer, you should have acid and base, and both should be weak. So that means you should have a weak acid and its conjugate base, or a weak base and its conjugate acid. There should be a weak and conjugate each other. You should have acid and base which are conjugate. Acid and base, and they must be conjugate of each other. So now let's check whether we have ammonium chloride and sodium hydroxide. Why do they form a buffer, and the ammonia and the sodium hydroxide, they don't form a buffer? What do we have in ammonium chloride? That in ammonium chloride you have the ammonium ion, because the chlorine is very weak, do not participate in equilibrium. So here we have the ammonium ion, and the ammonium is a weak acid. That means here, from here, we know that we are having the acid. But for us to get a buffer, we should get its conjugate base. What is the conjugate base of the acid, of the ammonium? That will be ammonia. So we need to check whether if we take ammonia plus sodium hydroxide, if we take ammonium plus sodium hydroxide, we need to check whether we get the ammonia, which is a conjugate base of the ammonium. So let's see, if we take the sodium hydroxide, we obtain the hydroxide. That means hydroxide is the one which is going to react with the ammonium. You can see that after reaction between ammonium and the hydroxide, we produce the ammonia. So with this system of ammonium chloride and sodium hydroxide, we'll be having a mixture of ammonium and ammonia. This is a weak acid and a conjugate base. In this case, we are having a buffer solution. So we have here a system here which is a buffer solution. We have a mixture of ammonium and ammonia, and this is the buffer solution. What else if we are having a buffer? We are having now ammonia and sodium hydroxide. Do we have a buffer? That's what we need to check. Here the ammonia, we have the ammonia, and sodium hydroxide, you have hydroxide. If you react with ammonia and the hydroxide, you don't produce the ammonium. So that means here we don't have a buffer. This is a base and this is a base. No conjugate acid can be formed. That is the reason why you cannot form the buffer solution made by ammonia and sodium hydroxide, but you can form a buffer made with ammonium chloride and sodium hydroxide. That was question number 11. Let's quickly go to question number 12. Question number 12 is saying, what is the H plus, or the hydronium ion, in a solution of 0.25 molar acetic acid and 0.03 molar sodium acetate? Here we have the acid, the weak acid, and its salt. Automatically you have a buffer. So we should use the IC table to see how to solve the buffer. So this is the system that we have. We have acetic acid and you have the sodium acetate. It will give the acetate ion. So then here we can have 0.25 of this one, and here we have 0.03 of this one. The hydrogen we don't have, because a buffer solution has this system and this system. This one you have concentration, this one you have concentration, it was given. Then we can solve for hydrogen. Then after solving for hydrogen, we determine the pH, but here they didn't ask the pH, they asked only to determine the H plus. So that means Ka will be equal to this one, this one. So that means 0.03 plus x times x over 0.25 minus x. So if we can assume the x as negligible, we are assuming this one negligible and this one negligible. Now what do we have? In this case we have, this is the Ka that was given, is equal to, here we have 0.03 times x, because this one will be negligible, over 0.25 because this one will be negligible. In this case we will get x is equal to 0.00015 molar. But if you have made the assumption, you need to check whether the assumption is valid. Here, percentage dissociation is equal to this one, the one dissociated dividing with the initial one, 0.25 times 100. We get 0.06%. In this case, because it is less than 5, assumption is valid. Then you can say that the hydrogen concentration or H, the hydronium concentration is equal to 1.5 times 10 power negative 4 molar. Let's quickly move to question 13. Question 13 is what is it asking? It is asking that also it is requesting to determine the H plus or hydronium ion in a solution of 0.075 molar, the HNO2 and 0.03 molar sodium nitrite. So here also we have a buffer because we have this one and salt. This is the acid and this is salt. It's the same. We need to use the same concept that we have used in the previous question. We have this one and the concentration were given. Then we use the quadratic equation to solve the x, but we need also to do the assumption, but we need to verify the assumption here. The percentage dissociation is equal to 0.15. That means here assumption is valid. Then we can say that the H plus is equal to 1.13 times 10 power negative 4 molar. Now let's move to another question. What is the next question? Next question is question 14. Question 14 is saying what is the hydroxide in the solution of this one. You can see this is the base and its salt. So here then you have also a buffer, a solution. Then they're asking the hydroxide. So in this case we can use the IC table. So we have this one and you have this one. The concentration were given. Then here we have the hydroxide. So that means for the base they accepted a proton to become NH3 plus and liberate the hydroxide in the solution. Here we are determining the hydroxide. So we also use the to solve the equation by doing this assumption that this one is negligible and this one negligible. Then we solve for x. That means x will be equal to the concentration of hydroxide. We need also to check for the assumption whether it is valid. You can see here that it is valid. The percentage dissociation is 0.35%, is less than 5%. In this case, we are going to say that hydroxide concentration is equal to 4.23 times 10 power negative 4 molar. So we are moving quickly to question 15. Question 15, what is it asking? It is saying what is the hydroxide concentration is the solution of 1.25 molar ammonia and 0.78 molar ammonium nitrate. Here also we have a base, a weak base, and salt. That means we have a buffer. We also use the same logic of the IC table to check for the hydroxide. So we assume x as negligible, and also we check for the assumption. After getting x, you calculate the percentage dissociation. You see that the percentage dissociation is 0.0023%. Here, the assumption is valid, and we have the hydroxide concentration is equal to 2.88 times 10 power negative 5 molar. Let's quickly move to question 16. Question 16 is asking, saying what concentration of ammonium nitrate is required to make the OH minus is equal to 1 times 10 power negative 5 in 0.2 molar solution of ammonia. You can see here we have the solution ammonia 0.2. This is the base, and you have its salt, which is ammonium nitrate. They're asking now what will be the concentration of this one, so that we will be having the hydroxide, which is equal to this one. Here also we need to use the IC table to construct the buffer system. The problem is that here we don't have the ammonium nitrate here. That means here it will be Y. We don't have this amount which is there initially. This one we know. Then the remaining one, that means will be Y plus X, because the one which is initially plus X, now we need to determine this Y. That's what they're asking, how much this one. What is the quantity of ammonium plus or ammonium nitrate which were there before, so that we can get the X was given. That means the hydroxide was given, that is X, then you can add it and determine Y. That means here we have the percentage dissociation. The X is equal to 1 times 10 power negative 5. This X we get it from the hydroxide, because the hydroxide was given. The percentage dissociation, that means we take this one, X dissociate divided with 0.2, we get less than 5%, the assumption is valid. So we make X negligible as compared to 0.2 or to Y. That means in this case, if assumption is valid, that means we can make this X negligible and this X negligible. So in this case, we will have the y times x, because this one will be negligible, over 0.2. Then you can determine this one, you have it, and x you have it. Then you can determine the initial amount of ammonium nitrate. That means we'll be having 0.36 molar as the concentration of ammonium nitrate required, so that we can have the hydroxide, which is equal to 1 times 10 power negative 5 molar in this buffer C system. So I'm quickly moving question 17. If you have any problem, you can ask me, you can stop me and ask question if you don't understand. But the questions, they are very easy, they are not difficult, so you can even solve yourself. But if you don't understand anything, please send me a message saying I don't understand this step. Then I will reply to you immediately. I stop and reply to you. So question 17 is saying what concentration of sodium fluoride required to make H plus 2.3 times 10 power negative 4. Here H plus was given in 0.3 molar solution of HF. Here also we have the salt and the acid. Now they are asking the concentration of the salt. We do the same system as we have done for the previous exercise. So what we don't know is this one, the sodium, the fluoride, sodium fluoride, which were there initially, so that we can combine with HF, so that we can produce such amount of H plus. In this case, we use the X was given, that means the H plus. We also see whether the assumption is valid. Yes, the assumption is valid because it is less than 5%. So if we can assume that the X negligible, because here the assumption is valid. So that means we get here this one become negligible, this one also become negligible. That means Ka is equal to y times x over 0.3, and x is equal to a concentration of H plus. X was given, then you can determine the required amount of sodium fluoride, so that we can get this amount of x. Here we get the 0.86 molar. So I'm moving again very fast, because the exercises are very easy. You can solve and try solving yourself. Let's see question 18. Question 1.8 is saying what's the effect on the concentration of acetic acid, effect on acetic acid, hydronium ion, and the acetate ion when the following are added to acidic buffer solution of equal concentration of acetic acid and sodium acetate. Then, so we have the buffer solution which has the acetic acid and the acetate. They have equal concentration, and they are asking what happens if you add an acetic acid. What will happen if you are adding? What will happen to acetic acid, hydronium ion to acetate when you are adding the following component? When you are adding HCl, when you are adding CH3COOH potassium, when you are adding sodium chloride, when you add potassium hydroxide, and when you are adding the CH3COOH. That's what they're asking. What will be the effect on this buffer? If you have this buffer made of acetic acid and sodium acetate, what will happen when you add the following chemical to the buffer system? Let's see, this question is theoretical. We don't need to calculate. Here we have a mixture of acetic acid, acetate ion, and the H plus. So what will happen if you add acid? This is the mixture that you have. We have this one. What will happen now? We have the acetic acid, we have the acetate, and we have the hydrogen. That is what you have when you add the hydrogen. That means they added the hydrogen, they react with the acetate ion to produce the acetic acid. Here we will be increasing the acetic acid, and the acetate ion will be consumed, and here also hydrogen will increase because we will be adding the acid. So hydronium ion will slightly increase, that means the H plus will increase. Sodium acetate will decrease because you can see it will be consumed, to react with H plus from the acid, and the acetic acid will be increasing because the acetate will be reacting with hydrogen to form the acetic acid. So what will happen if we are adding the acetate ion? That means you have a mixture of this one and this one and this one. That means they added the acetate ion will increase the concentration of the acetate. So if you add the acetate, it will increase the concentration of acetate. That means we are adding the product to the reaction. Let's see, we have this kind of mixture, the acetic acid, which gives the acetate plus H plus. That's the mixture, the buffer solution that we are having. Now what will happen if you add the acetate? That means it's like adding the product. Acetate in the product, we are adding acetate. That means the acetate will increase the concentration of the product, the concentration of the acetate. Adding a product to the reaction will cause the reaction to shift to the left. That means if this one is increasing, you are increasing the product, the reaction will shift to what the formation of acetic acid. So that means here we have the reactant which are back for me. Acetic acid here will increase and hydronium ion are consumed. So that means here we are increasing the acetic acid. The hydrogen also will decrease because they will be reacting with by the added acetate ion. So here acetate ion will increase because we are adding them. Hydronium ion will decrease because they will be reacting with H plus and they will be reducing. Acetic acid will increase because the equilibrium will shift to the right. Then the equilibrium will shift from the right to the left to what the formation of reactant. Then in this case we are forming more acetic acid, then acetic acid will increase. So let's see if we add sodium chloride. So sodium chloride, it is just sodium and chlorine, so it will not have any change because it cannot even add, it cannot react with any of the chemical to change the equilibrium. So not change the concentration of hydronium ion, acetic ion or acetate ion when you are adding sodium chloride, because sodium is spectator ion and chlorine also is a spectator ion. Here we don't have any change. So here again, so the next question is asking when you add the hydroxide ion, so in the mixture, that means the hydroxide will react with H plus. That's what it means to produce water. So in this case, we are removing the hydronium, so that means we are removing the product. Here, that means when hydroxide reacts with the H plus, that means you are removing the hydrogen or hydronium ion. That means you are removing the product, and if you are remove the product, that means the reactant will react to give the product. That means acetic acid and acetate ion will increase. So here we have the acetic acid will decrease because the equilibrium will shift from left to right. So that means this one will be decreasing, acetic acid will decrease, but this one, acetate, will increase. Of course, here the hydrogen will be decreasing because they are going to be reacting with the added hydroxide. That is what it means. So hydronium ion will decrease because they will be reacting with hydroxide. Acetic acid, the acetic acid will decrease because the reaction will move from this one this way to this one. Then you have the acetate ion which will increase, it will be produced. So that is what will happen when you are adding hydroxide. So again, we have a mixture of this one and this one, this one. They're asking when you add acetic acid here, you are adding the reactant. If you add more reactant, that means the equilibrium will shift toward the formation of the product. Hydronium ion will increase. Here, that means the product will increase. Acetic acid is also going to, acetic acid will, so we are adding the acetic acid to increase. Then here also acetate ion will increase. So that is what will happen. We're adding acetic acid, we're adding the reactant. That means this one will increase, but this one also will increase because it will shift toward the formation of the product. The reactant will form the product. This one also will increase because it is also the product. Then that was that question. Then let's go to question 1.9. Question 1.9 is saying what's the effect of the concentration of ammonia, hydroxide ion, and ammonium hydroxide when the following are added to the basic buffer. It's the same question like we have done the previous, except that here we have a basic buffer of ammonia and ammonium nitrate. Let's go quickly. We have this system, and what is if you are adding, we have a mixture of ammonia and ammonium and hydroxide. When you add the Ki, so that means you can see there is no hydroxide or proton, so we have no effect on the amount of ammonia and ammonium or hydroxide because both potassium and iodide are spectator ion, they don't react. So when you add ammonia, that means we are adding here the ammonia. Ammonia will increase. We are increasing the reactant. This is like adding the reactant. The direction will shift to the right. That means we have more formation of ammonium, and you have also more formation of hydroxide. Ammonia will increase, ammonium will increase, and hydroxide will increase. So what is if we add Hi? That means we're adding the more proton. So more proton, they react with a base. That means we have increasing the hydrogen in the solution, and the hydrogen in the solution react with hydroxide. So that means hydrogen react with hydroxide to form water. That means hydroxide will be decreasing. This is like removing the product. If you remove the product, there will be formation of more product. The reaction will shift to the right, decreasing the ammonia and increasing the ammonium. So here the hydroxide will decrease because they are reacting with H+. Ammonium will increase because the hydroxide will be removing, and the more formation of the product will be taken place. So that means we, after removing the product, they have more formation of the product. That means the ammonium will increase, and the ammonia will decrease because it will be ammonia will be transforming into product. So we continue on theoretical question. So this one is asking when what happens you add sodium hydroxide, you're adding hydroxide. So that means sodium hydroxide will increase the hydroxide. So this is like adding the product. If you add the product, the reactor shifts toward the formation of the reactant. This will shift the equilibrium to the left. That means the ammonium will be consumed. It will decrease to form the ammonia, and the ammonia will increase. Hydroxide will also increase. Ammonium will decrease, and ammonia will increase. So what is if you add ammonium chloride? That means you're also adding the ammonium. That means you are adding the product. So adding the product because the reaction to shift toward the formation of the reactant. That means ammonia will increase. Ammonium will increase also because it is being added, and the hydroxide will decrease because they are going to be consumed by giving the back the reactant. Let's take some water. Then we start on question number 20. Just a small time pause for taking water. Okay. Now we are moving to question 20. Question 20 says what will be the pH of a buffer solution prepared from 0.2 molar ammonia and 0.4 molar ammonium, and just enough water to give 1 liter of solution. This is a buffer solution system. We use the IC table to solve the X dissociated. So we have 0.2 molar, here we have 0.2 molar, 0.2 molar, 0.4 molar, then we solve for X. Here we assume the X negligible, and we check the percentage dissociation. So here the assumption is valid. So that means the hydroxide will be equal to 9 times 10 to the power negative 6 mole. So the assumption is valid. Then after getting the hydroxide, you can determine the pOH by taking negative log of hydroxide concentration. Here we have 5.046. Then you determine the pH by taking 14 negative pOH. Then we get a pH of 8.95. We are moving to question 21. Question 21 saying calculate the pH of buffer solution prepared by 0.15 molar phosphoric acid and 0.25 mole of potassium hydrogen phosphate and enough water to make 0.5 liter. That means we can divide with 0.5 liter to find the mole of phosphoric acid, the molarity of phosphoric acid, and the molarity of potassium hydrogen phosphate. Then we do the buffer system composed of this acid and the salt. So they are saying assume the hydrogen from secondary side dissociation as negligible. That means the one which you determine the pH is the first dissociation of phosphoric acid, which means we need only the Ka1. That is what will happen in the first dissociation. The volume is 0.5 liter. Then we determine the molarity by taking the mole over the volume in liter. So here we get 0.5 0.5 mole per 0.5 liter, we get 0.5 molar. Then we have a system with 0.5 molar this one and 0.31 molar of acid. So that is what will happen, 0.31, 0.5. Here we have the X. Then we solve for the X, which is the hydrogen, which will be dissociated. We have the percent dissociation, which will be equal 1.38. That means the assumption is valid. We have then X, or which is equal to, or hydrogen, which is equal to 0.004278. Then the pH will be equal to negative log of H plus. We'll be having 2.37 as the pH of this mixture. Question 22. Because that was question 21, so we need to see question 22. Question 22 is saying how much solid sodium, this one, then it must be added to 0.3 liter of 0.5 molar acetic acid. So we have the acetic acid and its salt, but this one was given to 0.5 molar acetic acid. And here how much solid, this is the salt, must be added to 0.3 liter, 0.5 molar acetic acid. So here we don't have the concentration. To give a buffer solution of pH of 5. Meaning if the pH was given, so we have the H plus dissociated in this system, in this buffer system. They are saying assume negligible change in volume as the solid is added and the Ka value was given. So here we need to see what was the molarity, the concentration, what was the initial concentration of the salt. So we use also the same system, the buffer system, but what you need to know is that we have here 0.5, here we don't have the salt content, we don't have. Then we are going to solve this one, y, and then after getting the molarity we can get the number of mole, and after getting the number of mole we can determine the mass. So here we have Ka, then we can make it, we check from the dissociation. Here we can make it negligible, so y times x over 0.5. Then we get is the concentration, we calculate it from the pH. After getting the pH is equal to 5, H plus equal to 10 power negative 5, then we can see that y will be equal to 0.9, so molar. Then after getting the molarity of this one of the salt, then more of the salt is equal to, after getting the molarity you can multiply with the volume, because we have 0.3 liter, then you have 0.27 moles. After getting the moles, then you multiply with the molar mass to get the mass. 0.7 mole of acetic acid of this one as is equal to mole of this salt. Then in this case we can determine the molar mass, get this molar mass. Then after getting to see the mass, we take the moles times the molar mass. What we have done is that we have determined this y in molarity, so we get 0.9 molar. After getting the molarity, we determine the moles, because we have the volume which is 0.3 liter. Then after getting the moles, then we have multiplied with the molar mass to get the mass of this salt, which is required to form a buffer with this pH. Question 23, question 2.3 is saying what mass of ammonium chloride must be added to 0.75 liter of 0.1 molar solution of ammonia. So here also is the same. To give a buffer solution with this pH, assume a negligible change in volume as the solid is added. So it's the same as question, so we also sort for the initial value of ammonium, so that will be also the same concentration of ammonium chloride and the same mole. So here then we make this one negligible and we solve for y. After getting y's, we get 0.099 molar. Then we check the number of mole by taking the molarity times the volume. We get this one, and after getting the moles, we multiply with the molar mass. The molar mass of ammonium chloride is this one. Then we multiply with the molar mass so that you can get the mass of ammonium chloride required, so that you can have a buffer solution of pH equal to 9.26. So we move to question 24. Question 24. What are they saying in question 24? They are saying the buffer solution is prepared from equal volume of 0.2 mole acetic acid and 0.6 mole sodium acetate. Then they are given, the Ka was given. They are saying use the Ka value of 1.8 times 10 power negative 5 as the Ka for acetic acid. What else they have given us? They are saying, then they are asking what is the pH of the solution. The solution acidic or basic. So what is the pH of solution? That is that when 3 milliliter of 0.034 mole HCl is added to 0.2 liter of this buffer. So here we have the system which is having 0.2 mole acetic acid and salt. Then you can calculate the pH. We need to do a buffer system IC table, and then you see how much dissociated. Then after getting how much dissociated, calculate the pH by taking pH is equal to negative log of H plus. So here we determine the H plus. After getting the H plus, then we determine the pH by taking negative log of H plus. We get 5.22 as the pH. But they are asking now what will be the pH if in this buffer system we are adding hydrogen chloride. The solution is acidic because we have the pH which is less than 7. Now the next sub question, they are asking what you add the HCl, what will happen to the pH when you add the HCl to this buffer system. That means the moles of acetate will be reacting with the mole of HCl. So here we have the mole of acetic acid, we have this one. We have also the mole of acetate. We have this one. Of course, we are taking the mole dividing with the volume that was given. So now we have the moles of HCl added. That means the HCl will react with the acetate. So then we can determine the mole of acetate remaining by taking the initial mole of acetate minus the HCl added, the mole of H plus added. That means remaining for this moles of acetate ion. That means then you can determine the concentration of acetate by dividing with the volume. That means the volume will be having 0.2. That's the volume, but we have added the 3 ml of the HCl. That means the volume will be now 0.203 liter. So we have added 0.2 liter plus 3 ml of the acid added. You get this one. That means you get the concentration. After getting the concentration of acetate, you also determine the concentration of acetic acid. So remaining acetic acid will be this one, dividing with the what will be remaining the total volume. Then after, then we are going to have this IC table to see what is H plus, which is going to be dissociated. So then we replace the values. Then we see the X, the H plus. In this case, this assumption is valid, and the H plus is equal to 6.01 times 10 power negative 6. Then for us, the pH is equal to negative log of this one, which is equal to 5.2 to 1. You can see we don't have much change in the pH because we have a buffer solution. Question 2.5. Question 2.5 is saying 5.36 gram of sample ammonium chloride was added 25 milliliter of 1 molar sodium hydroxide, and the resulting solution is 0.1 liter. What is the pH of this buffer solution? Here we have the buffer solution, which is ammonia and ammonium system. Is the solution acidic or basic? They are saying what's the pH of solution. That is that 23 ml of 0.034 molar HCl is added to the system. So now let's first find the buffer solution of this system before adding the HCl. Here we have the moles of ammonium chloride, so we take the mass dividing with the molar mass. We have also the moles of ammonium chloride is equal to mole of ammonium, so that means we have 0.1 mole. We determine also the mole of sodium hydroxide, so that will be equal to the mole of hydroxide, right? So we have also mole of hydroxide. Then you can determine the ammonium will react with hydroxide to form the ammonia, because that is the buffer system that will be having ammonium and the ammonia. So we have the remaining mole of ammonium, because here we have the mole of ammonium chloride. Then we have also the moles of ammonium chloride equal to the moles of ammonium, and you have also mole of sodium chloride, sodium hydroxide. And remember, this mole of sodium hydroxide they react with the mole of ammonium. Then we need to determine the remaining moles of ammonium. We have them by taking the initial moles minus the added mole of sodium hydroxide. Then in this case, we have the mole of ammonia formed, so that means here we will form 0.025 mole of ammonia. The mole of ammonia form will depend on the hydroxide that we have added. That means the mole of that means we'll be taking the ammonium plus hydroxide and we form the ammonia. That means the mole of ammonia will be the same as the mole of sodium hydroxide, which is reacted. Then we can determine the concentration of ammonia formed. Then we determine also the concentration of ammonium. So the main concentration of ammonium. Then you have a buffer solution of this one, the ammonia and the ammonium. So the trick here is to know that before having the buffer system, you will have a reaction between ammonium and the sodium hydroxide, then ammonium which will be remaining and the ammonia which will be produced. They are the one which form the buffer system. So then after getting this, we can then go to the table, which is the initial change equilibrium. We have the concentration of ammonia, we have the concentration of ammonium, then we determine the hydroxide, which is obtained at the end of dissociation. In this case, we have the hydroxide, which is equal to 6 times 10 power negative 3 molar. And then after getting the hydroxide, then you have the H plus by taking 10 power negative 14 over the hydroxide. That means the H plus is equal to 10 power negative 14 over the concentration of hydroxide that we have calculated here. Then you have this one. Then you can calculate the pH is equal to negative root of H plus. We have 8.778. What will happen to the pH then when the HCl is added? That's what they are asking here. The solution is basic, of course, because we have a more than 7 pH. So what will happen then when the HCl is added? So that means the HCl will react with ammonia. It is acid reactive for ammonia. That means here the ammonia will decrease. So the moles of ammonia, the mole of H added, we get them. Then the moles of ammonia remaining, that means the reactive for the HCl, the one which will be remaining is this one. Then we determine the concentration of ammonia by taking these remaining moles, dividing with the total volume. Of course, the total volume we need to add also the 3 ml that was added for the acid. Then we will get this 0.2417. We also determine the concentration of ammonium. Also, ammonium will be in the total solution. That's why you can see we are taking 0.075 dividing with this one, because they will be in the total solution. Then we will be having this one. After getting this one, then we solve for hydroxide. So that's what will happen for hydroxide. We get the hydroxide. After getting hydroxide, we get the H plus. After getting the H plus, then we do negative log of H plus. We find the pH is equal to 8.776. You can see here we don't have much change in the pH because also we are having a buffer system. No much change in the pH because it is a buffer solution. So let's go to question 2.6. Question 2.6 saying the saccharin C7H4N is a weak acid, so it has this Ka. If 0.25 liter of diet cola with a buffered pH of 5.48 was prepared from 2 times 10 power negative 6 grams of sodium saccharide, what are the final concentration of saccharin and sodium saccharin in the solution? Here now they are saying we have the saccharin, so which is a weak acid. Then they are saying if 0.25 liter of this diet cola with buffered, this one the pH was given, was prepared from this one sodium saccharide, that means it's salt, sodium saccharide. Then what are the final concentration of saccharin and the sodium saccharide solution? That is what they are asking. What will be the concentration of saccharin and the concentration of saccharide the solution? That means we need to determine concentration of this one, the concentration with salt. Of course, the pH here was given, and here we have also the buffer solution system. The volume was also given, and we have the Ka. Let's go quickly to the answer. We have this one which is dissociated to give H plus, to give this one. So then the molar mass of sodium saccharide was given. You can determine it from the individual molar mass. We have also more of sodium saccharide. So here also you can take the mass over the molar mass because sodium saccharide was given. after getting the mole, you can determine the concentration by taking the mole dividing with the volume. Now you have the concentration of the salt. After getting the concentration of the salt, you can see according to the equation, the concentration of saccharide ion is equal to the concentration of saccharine. You can see here, if it will dissociate, the concentration of this acid will be equal to the concentration of the salt. That means here also we have the concentration is equal to the concentration of the salt, and here we have it. Then we be having the system IC table. Here we have the acid, and here we have the salt. In this case, then you can determine the X. Then after getting the X, then we have X. We have it. pH is equal to 5.48. The X is equal to H plus is equal to 10.5.48. That's equal to 3.31 times 10.6 more. That means this one will be equal to this one negative X. Equal to also this one negative X, because X we have it. Then what will happen is that this also will be equal to this one plus X. That means you have this one. So then you get the concentration of this one and the concentration of this one. Let's see question 2.7. Question 2.7, what is it asking? Saying what's the pH of 1 liter of solution of 100 grams of glutamic acid. We have the glutamic acid, the diprotic acid, to which has been added 20 grams of sodium hydroxide during the preparation of monosodium glutamate, the flavoring agent. Assume that the mass of sodium hydroxide will not change the volume. They are also asking what is the pH when exactly 1 mole of sodium per mole of acid has been added. Then here you have also calculated also the pH when 32 grams of sodium hydroxide has been added. Here we need to calculate first the pH when the sodium hydroxide, when the sodium hydroxide was not equal to the, when the mole of sodium hydroxide are not equal to the mole of glutamic acid, that is number I. Then for the second one, to determine the pH when they are equal, when the moles of glutamic acid are equal to the mole of sodium hydroxide. Then sub-question number 3 is saying, then here we need to calculate the pH when the moles of sodium hydroxide are more than the moles of glutamic acid. Let's see the answer starting from the sub-question. Glutamic is a weak acid and sodium hydroxide is a strong base. We need to see what are the number of moles which will be remaining. You have more of glutamic acid. Here also the more of sodium hydroxide, you have it. Now remaining more of weak acid, we do the difference. We remain with this one. That means when they react, they form the weak acid that will be remaining the solution. And also we have the salt which will be formed. So that means the concentration of weak acid will remain with will be 0.18 per liter, because we have 1 liter solution. Then the concentration of sodium glutamate, that will be equal to the concentration of sodium hydroxide which is reacted. We have also 0.5 more over this one. Then you have the buffer system. So we have a mixture of weak acid and salt. Then you can have this one, and also this is the salt. Then after getting, then you can use the IC table. We have glutamic and its salt. Then we determine the X. We do the same as we did. We obtain % dissociation. You get X is equal to 3.06 times 10⁻⁵, and this will be the pH. It will be 7.51. The second sub-question is saying when the moles of sodium hydroxide are equal to the mole of glutamic acid, this will be after addition of 27.2 grams of sodium hydroxide. In this case, we will be having the same number of moles. Then if you have the same number of moles, we determine the pKa. This will be equal to negative log of Ka1. This will be equal to negative log of Ka2. Then after getting the pK, that's how we calculate the pH when there is full the moles of the mole of weak acid are equal to the moles of a strong base. When you have a polyprotic acid, that is how we calculate the pH. pH will be equal to 1/2 pKa1 plus pKa2. In this case, we have 6.77. Let's go after adding the 27.7 grams of sodium hydroxide or glutamic acid. They have transformed into the dissociated form. That means we are transforming all the glutamic acid into the first dissociated form. That means we transform this one into this one. But looking on this one, we are still having the hydrogen which is waiting to be dissociated. So, but the 27.7 grams of sodium hydroxide, that is what we add, so that this acid, diprotic acid, is transformed into this one. So that means only the first dissociation is giving this one. We will be using this one. So we are remaining then with 0.68 mole of this one. That means this one is 1 mole and this one. That means all 0.68 moles has transformed into this form. That means after adding 27.7 grams, we are remaining with 0.68 mole of this form, the one which is from the first dissociation. To get 32, then we need to add 32 4.8 grams. That means 27.2, they will change the glutamic acid to the its first dissociated form. Then this one we can add extra 4.8 grams of sodium hydroxide. So that means we add 4.8 grams of sodium hydroxide after adding this one of sodium hydroxide. How many more? So that means 27.2 grams of sodium hydroxide will contribute to the change of glutamic acid to its dissociated form. Then this one will react with the dissociated form. So now the more of glutamic acid we have them. In this case, we are no longer having glutamic acid, we have the more of glutamate, because all glutamic acid has transformed to a glutamate ion. Then you have 0.68 more. Now we determine also the more of sodium hydroxide, but we are determining only the moles for 4.8 mole, because the 27.2 mole they have contributed to the change of the glutamic acid to glutamate ion. Then remaining more of glutamate ion, so that means they added extra, we react with the moles, we remain with this 0.56 mole of glutamate ion. Then we formed more of sodium glutamate. That means here we form the sodium, the sodium salt, because we have this one reacting with the glutamate reacting with sodium. In this case, we have the sodium 2 glutamate, so we have this one. Then we have a mixture of glutamate ion and this ion, this salt. Concentration of glutamate, we determine the glutamate concentration, we also determine the concentration of the salt. We also get it. Then we just use the buffer system. You have glutamate ion and this salt. Then so here I have 0.56, here you have 0.12. Then we will be having this system, and then you calculate the H. We get the H, the percent dissociation is okay. Then we get the pH equal to negative log of H, which will be equal to 8.8.